Myself, Mrs. Rashmi G.P, Assistant Professor, Department of ECE, Nagarjuna College of Engineering and Technology. Today we are going to discuss logic gates, which are the basic building blocks of the digital logic circuit or digital electronics. Let us start with the basic gates. Those are NOT, and OR gates. And we are also discussing about the universal gates. Those are NAND and NOR. We are also discussing about XOR and XNOR gate. So let's begin with NOT gate. The symbol for the NOT gate is a triangle pointed towards the right, you can say, along with a bubble. So NOT gate is the only gate which has single input and single output. That is, it has single input and single output. Let us consider A as the input and Y as the output. So the possible inputs are, in the logic gates, the possible inputs are only the binary bits. That is, you can either give 0 or 1, which are also said to be 0 is said to be low and 1 is said to be high. And they are also called as truth and false. So let us consider it as the input and Y as the output. If I give a 0, the output will be 1. That is, just the complement of the input will be your output. And if I give a 1, the output will be 0. So if I give a 0 here, the output will be 1. And if I give a 1 here, the output will be 0. And as I told, this is the only gate which has single input and single out. Let us discuss about the next gate, that is the OR gate. Where the symbol is, the minimum input for the OR gate is 2. That is, if you consider A and B as the inputs and Y as the output, the truth table looks like this. Since there are two inputs, those are A and B, and Y is the output, for the OR gate, the possible inputs are 0, 0, 0, 1, 1, 0, and 1, 1. For this, the output, what we get out of the OR gate is 0, 0 will be 0, 0, 1 will be 1, 1, 0 will be 1, 1, 1 will be 1. That is, whenever, if at least one of the input is high, the output will go high. If all the inputs are low, the output will go low. Low in the sense 0, high in the sense 1. So the expression for the OR gate is Y is equal to A plus B, where the plus indicates the OR operation in the logic gates. And for the expression for the NOT gate is Y is equal to A bar, you can say. So let's discuss the NOR gate, which is just the extension of the OR gate. That is, if you just extend this gate with a NOT gate, if you add a NOT gate to the output of the OR gate, that will be your NOR gate. So the function of the NOT gate is to complement the input. Hence, the output will be Y bar. So if this is the output of the OR gate, the output of the NOR gate would be just the inverse of it. That is the Y bar, which is 1, 0, 0, 0. So the symbol for the NOR gate would be a OR gate with a bubble, which represents that it is a NOR gate which has minimum of 2 inputs, and the output will be Y bar. If you consider Y as the output of the OR gate, then Y bar will be the output of the NOR gate. So now let's discuss how the AND gate functions. The symbol for the AND gate would be, if I consider A and B as the inputs and Y as the output, the expression would be Y is equal to A dot B, where the dot is representing the AND operation. Coming to the truth table, if A and B are the two inputs and Y is the output, the possible inputs are 0, 0, 0, 1, 1 0 and 1 1, and the output we can expect out of the AND gate is 0 0 will be 0, 0 1 will be 0, 1 0 will be 0, and 1 1 will be 1. That is, as we can see here, whenever all the inputs are high, the output will be high for the AND gate. So this would be the Boolean expression for the AND gate. So let's discuss about the NAND gate, which is just the inverse of the AND gate. That is, it is the extension of the AND gate where you are just adding a NOT gate to the output of the AND gate, where it will inverse the AND gate output. So the truth table would be Y bar will be the output. That is just the inverse of it. The output for the AND gate is 0, where the NAND gate would be 1. Similarly, for all this, whenever the output is 1, the output will go 0 for the NAND gate. So the expression for the NAND gate would be Y is equal to A dot B whole bar, which is representing that the whatever the AND operations output is there, it is invert. So the next gate we are discussing is XOR gate. The symbol for the XOR gate looks like this. With a minimum of 2 inputs and 1 output, if I consider A and B as the input and Y as the output, the expression would be Y is equal to A exclusive B. So this symbol is representing that there is exclusive operation. It is exclusive representation. Then the truth table would be A, B and are the inputs and Y is the output, where Y is doing the exclusive OR operation. So if I take the inputs, the possible inputs are 0 0, 0 1, 1 0, 1 1. This table is representing the truth table for the exclusive OR operation. So if there are odd number of ones in the input, the output will go high. So 0. Since there is an odd number of 1, the output will be high, again high, and this will be 0. So this is how the exclusive OR gate functions. The exclusive NOR gate would be just the inverse of the exclusive OR gate. That is, if you add a NOT gate as an extension for the exclusive OR gate, it will be functioning as a exclusive NOR gate, and the output Boolean expression would be just the inverse of the exclusive OR, and the truth table we can extend as, since it is just the inverse, we can just inverse it, that is, it will become 1 0 0 1. So these are the basic logic gates which we have discussed today. That is, NOT, OR and AND are the basic logic gates. NAND and NOR are called the universal gates, since we can design the logic circuit for any of the Boolean expression given, and there are XOR and XNOR gates. So now let us discuss using these gates how we can design an half adder and a full adder. Here we are combining few of the gates and designing a circuit like half adder and a full adder. So that is called combinational logic circuit. So now let's see how we can design a half adder. An half adder is a circuit where it will add 2 binary digits. We are adding 2 binary digits. For example, A and B are the 2 binary digits. The output will be Y if you sum will be the output. And there will be the output, another output would be carry. So out of the addition, we will get a sum and a carry. So those are represented in the truth table. What are the possible inputs when there are 2 binary digits? 0 0 0 1 1 0 1 1. So the sum for this would be 0 plus 0 would be 0, where the carry will be remaining as 0. 0 plus 1 would be 1, the carry will be 0. 1 plus 0 would be 1, carry will be 0. 1 plus 1 would be, if you do the binary addition, 1 plus 1 would be 2, where the binary of the 2 is 1, 0. Hence, this 0 will be here and we have a carry of 1. So, this is the truth table for the half adder. Seeing the truth table, I have to design the combinational logic circuit, that is using the basic gates or the gates which we have discussed. We are going to design the half adder circuit using this truth table. So let us see which basic gates would be more suitable for the sum part. As we can see here, the output of the sum, that is the sum is going high whenever there are odd number of ones. So that means we need a XOR gate here, one XOR gate, and the carry is going high. It is more suitable, as you can see here. That is, if you refer the truth table of the AND gate, it is the replica of the AND gate. That is, the output is going high when all the inputs are high. Hence, we need a AND gate. We need one AND gate and one XOR gate. So, let us design the circuit of the half adder. So, as we have said, we need one XOR gate with A and B as the input, and the output of this is sum, that is equal to A exclusive B, and the carry part is AND, that is an AND gate. This is the carry we are getting. So the carry, for the carry the inputs are again the same, that is A and B. So this, that is a combination of these two gates, that is exclusive OR along with the AND gate, is giving us the half adder design. Coming to the full adder, full adder is used to add 3 binary bits, that is the inputs would be A, B and C. The output will be sum and a carry. What are the probable inputs? 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0 and 1, 1, 1. These are the possible inputs if there are 3 bits. Coming to the sum, 0 plus 0 plus 0 would be 0, carry would be 0. This will be 1, carry 0, again 1, 0. 1 plus 0 would be 2. And the binary representation of 2 will be 1, 0. So we are keeping the 0 here and the carry. Again 1, 0. Again there is 1 plus 0 plus 1, which is 1, 0, that is 2. So keeping the 0 here and the carry 1, 0, 1, and 1 plus 1 will be 3. The binary representation of 3 is 1, 1. Hence we are keeping the 1 here and the carry part here. So, with reference to this truth table, now we have to build the full adder circuit or full adder design using the logic gates. Let us see which would be the suitable gate to implement this. First, let us see the sum part. As we can see here, the most suitable would be whenever there are odd number of ones, the output, that is the sum is going high. Hence, we need an XOR gate. XOR gate with 3 inputs. Since we have 3 inputs here, we need an XOR gate which will be having 3 inputs. That is an XOR gate with 3 inputs with A, B, C as input. The output, that is the sum, will be A exclusive, B exclusive, C. So the sum part is done now. Coming to the carry part, as we can see, it is not, we won't be able to directly implement any of the gates here. Hence we have to simplify this equation. How do we simplify is, check whenever the carry is high and write the Boolean expression and simplify. How do we write is carry is equal to, the carry is going high when B and C are high. So I'll write B, C here plus, the carry is again going high when A and C are high. AC plus again AB plus ABC. So let us simplify this. BC plus AC plus, we can take out AB as common and keep 1 plus C. 1 plus C is nothing but 1. Hence, the equation can be simplified and written as AB plus BC plus AC. That is, AB plus, the carry equation is AB plus BC plus AC. By seeing this expression, what we understand is AB, which is nothing but A dot B, that is the AND operation. BC is again the AND operation. AC is again the AND operation. Hence, we need 3 AND gates to AND A and B, B and C, A and C. So, we need 3 AND gates, and we have the OR operation here, which is denoted by the plus symbol. So, we need 1 3 input OR gate. OR gate. So, let us extend our circuit here. B and C and A and C. That is, you can directly take this as inputs, or else you can represent here also B, C and C, A. So, these are the inputs, and combined with that, the performance of OR operation is done with the 3 input OR gate. This will give you the carry. So, the carry equation is AB plus BC plus CA. So, together this is a combinational logic circuit for full adder. In this way, for any of the Boolean expression using the gates, we can design the combinational logic circuits. So, as we discussed, the basic logic gates, that is NOT, OR and AND, and the universal logic gates NAND and NOR, XOR and XNOR, with the symbol, expression and the Boolean expression and the truth table. And also we have learned the combinational logic circuit design, that is the designing of half adder and full adder with the help of the truth table, how we are going to see which gate would be suitable for designing of the half adder and the full adder. So,